Good day and welcome back to our third video discussing the dot product. In the previous two videos, we introduced kind of the definition of the dot product and saw a whole bunch of different properties. And what we'd like to do in this video is explore just one application. And that application is going to be associated with the physical concept of work. And let me just give you kind of the quick recall. And if we are in class and I asked you, what is work? Immediately a bunch of you would either raise your hand or just hopefully yell out at me. Work is force times distance. So we typically think work is something to do with F times G. So let's go ahead and see if we can put that in terms of what we've been talking about and dealing with things here in three-dimensional space. So suppose a constant force F moves an object from a point P to a point Q. So I'm once again going to just draw this kind of horizontally to make it look a little bit nicer. And what we're thinking is we have some object at the point P. So say you have maybe a desk or a dresser or something you want to move, and we're going to start pushing it. And when we push it, we're using some force vector that we're creating. We're assuming we're pushing it with a constant force. And no matter how much we'd like to think we're pushing directly in that direction we would like it to go, that's not always going to occur. Maybe that force vector is going a little bit off here above in the picture. So the question is, how much work is done by this force as we move the object that's at P all the way over to Q? And it turns out that it's going to be the product of the component of F along D and the distance that we move. So I'm going to introduce just a bit of notation here. So I'm going to let the vector D, and D stands for displacement, be the vector going from P to Q. And I'm also going to just remind you, if we drop down kind of a perpendicular, then the component of F along D is going to be given by the magnitude of F cosine of theta, similar to what we were talking about with the projections in the last video. So what this gives us is that the work done is the product of that component. So it's a product of magnitude F cosine theta multiplied by the total distance moved. So the magnitude of D. So note we have three numbers we're multiplying together. The order that we multiply numbers together does not matter. So this could be magnitude of F, magnitude of D, cosine of theta, which is precisely this geometric definition of the dot product we encountered in the first video. That is, this is really F dotted with D. So previously we thought of work as being force times distance. Well, in our context, we're going to think of work as being force dotted with displacement. And this is a concept that we will revisit again towards the end of the semester. But for now, let's look at a basic example. Let's calculate the work done by the force vector given here as it moves an object from the point 230 to the point 4915. And to calculate this work, what we need to do is take the dot product of the force vector, which we have, with the displacement vector, where the displacement vector would be the vector that takes us from the point 230 to the vector 4915, a concept we discussed in that previous section dealing with vectors. We simply need to think, if we're at one of these coordinates, how do we travel to get to the other? So in that x coordinate, we need to go from 2 to 4. So the first component of the displacement vector should be 2. In terms of the y coordinates, we need to go from 3 to 9. So the second component of the displacement vector should be 6. And then 0 to 15 in the z. So work is equal to force times distance. The force is a vector 10, 18, minus 6. And we're dotting this with the displacement 2, 6, 15. And I'll let you go through the details, but this ends up being 38. And a common question that I think I would get asked if we were, meeting face to face and we were in class is, what about, the units involved? And in this case, since we're not given any idea in terms of how we're measuring distance, say in meters, we don't have any units that we can put with this. So we would just leave it as a 38. But I'll note, if distance is measured in meters and force is in newtons, then work is in joules. But in a math class such as the one that we have here, I am not going to get too caught up in terms of the units. Things we'll have to be careful of is just to make sure that we're measuring distance in meters if force is given in newtons, or distance in feet if force is given in pounds. But in terms of the joules and labeling the units, I will leave that more to your physics-related courses. So that finishes up our discussion of the dot product. As a friendly reminder, if you have questions, do not hesitate to reach out to me, drop me an email, stop by our virtual office hours. I'm always happy to help and discuss math. So stay tuned and take care.